Okay, hello to everyone. The following project is about the design and simulation of a rooftop PV system for a university building. So this belongs to the course of renewable energy. So this is the outline of the presentation. First, we're going to talk about the objective, the project location, the load study, the PV system design. We have a Homer Pro simulation, the Homer Pro results. Uh, We have also the system dynamic simulation and protection. Finally, some conclusions and references. So this is the objective. The present project will focus on the design and simulation of a rooftop PV system to meet all energy needs of a university building located in St. John's, Newfoundland, which is Canada. In this case, we're going to utilize Homer Pro and MATLAB Simulink, and in order to design and simulate the system and control system by taking into consideration the energy load of the selected building. So, as I told you before, the project location is located in Canada, Newfoundland, and Labrador, St. John's. As you can see, here is the Google Maps locations, and if you want, you can check it on Google Maps. We're going to need a load study. In this case, we will be designing the system for a university building, and in this case, we have to take into account some kind of loads which are relating to lighting, which is referring to interior and exterior normal and emergency lighting. We have a appliance, which is related for general machines. We have space conditioning, water, if we are going to take into account water pumps and heaters and all that stuff. We have also a fire protection system. It's something that we need to take into account. We also take into account the transportation, such as elevators, and finally some data processing elements, which is related to university servers. So for the load calculation, we need to take into account we're going to use one floor connected load and some special connected loads. For one floor connected load, we get a total of 160 kilowatts. And for the special loads, we have a total of 120 kilowatts. We have to utilize these two kinds of loads. And we have, as for the connected total load, we have 600 kilowatts. In this case, we have to take into account that we are assuming a three-floor university building. Now we need to calculate the maximum demand, and for this case we're assuming a demand factor of 0.5, which gives us a total of 300 kilowatts. And we also are assuming a diversity factor of 1.2 as an average, which give us a maximum diversified demand of 250 kilowatts. So here we have the daily profile, the load profile of a university building, and this graphic is going to be uploaded in Homer Pro, this information, so we can have our simulation. So with this, we have the PV system design. Because we're dealing with a massive load for a university building, we're taking into consideration a grid-connected system. This kind of system give us a much more reliability and economic benefits. And also, this give us a returns of investment because we are able to sell back some energy to the grid. Also, this allow us to have an energy supply during the night or as a backup. We have as a solar source, we need to get all the data from the NASA server, and then we have to upload all this information in Homer Pro. So here's the system components. As you can see, here's the system architecture, which is composed of a PV panel. In this case, we selected a Paymar SG325P with a rated capacity of 1 kilowatt. Also, we have a grid connected system with a rate of 0.11 dollars per kilowatt hour. And also we have a generic converter of a capacity of 100 kilowatts capacity. This is because we need to convert the DC energy to AC. So here we have the Homer Pro results. So as you can see, at the end of the simulation we can get the operating costs, as you can see in the screen, as well as the excess of energy, and we have the electrical results. So as we can see, the total production related to the PV panels is like 77% of the total energy generator, and the other energy is purchased from the grid system, which is actually 23% of the total energy of the system. Also, we realize that the total energy generated during a year is like it's over 1 million, and we also are purchasing over 300,000 kilowatts hours per year of the grid connected for the grid system. And also, this amount of energy allows us an excess of electricity of a 89,000 kilowatts hours per year, which is like 6.25% of the total energy supply.
Here we'll talk about system dynamic simulation and protection. Our system dynamic simulation has been done using MATLAB Simulink. Our system consists of 10 arrays of PV panels, inverters, a filter circuit, and a transformer, which will be connected to our three-phase load. Every array, as usual, consists of many strings, and every string consists of many PV panels, and in our case, we have in every string 40 series PV panel and 5 parallel strings for every array. We have 10 arrays which will be connected in parallel, and every 2 arrays will be connected with an inverter. In the next slide, we will see our Simulink model for our system. In this slide, we can find the simulation model for our PV system. In the left side of the model, we have 2 variables, which are the solar irradiance and also the temperature, which are, in our case, for St. John's in the summer. Both of them are the main inputs for any PV array in our system. And as we know, any PV array generates DC power, not AC, but we need a 3-phase AC power to feed our load, which is, in our case, a university building. So we use inverters. Every 2 PV arrays are connected to one inverter, which takes the DC power and generate 3-phase AC power. Also, we use here passive filter to eliminate the harmonics, as we will see in the next slides, with also a 3-phase transformer to step up or step down the voltage as needed. So in the total, we have 5 inverters and 10 arrays connected with passive filter, 3-phase transformer, and at last some measurement tools with the 3-phase load. We used in our system 3-phase full bridge inverter, which contains 6 MOSFET transistors, and it's well known in the field of power electronics. In this slide, we can find the first try test with no load, and before using the passive filter, we can find huge distortion in every sine wave here. So it's not the expected results, and we need to eliminate this huge harmonics in our system. So we use the passive filter to eliminate this, and we will see that in the next slides. As we have just seen in the previous slide, we don't have a pure sinusoidal wave, but we need a pure one to supply our load. So it was very important to add a passive filter to eliminate these harmonics. This passive filter contains RLC components, which will be in specific values of capacitance, inductance, and also resistance. This is in order to adjust the wave and the voltage as we need. To test our simulation model, we had three cases. The first one no load, and the second one low load, and the final one full load with different irradiance and temperature values. In this slide, we find the PV output for all the cases. This output is a DC and from only one PV array. Here we start with the no-load test case with irradiance of 600 watt per meter squared and temperature of 20 Celsius. The difference between this model and the previous one is that we removed the load, so we connected directly the measurement tools to the load side of the transformer. In the next slides, we will see the waveforms of the output. Here we start with the inverter phase-to-phase output voltage. In the beginning, we can find some harmonics, but in the steady state now we have pure sine wave, and this is from the effect of the passive filter. Here we see the output of the load side of the transformer. In the beginning we have some harmonics, but in the steady state we eliminated it with the passive filter. So now we have pure sine wave three-phase voltage. The second test case here is a full load with a radiance of 400 watt per meter squared and temperature of 25 Celsius. And this is the final model for our system. Here we will talk about inverter phase-to-phase voltage. We can see that we started the time from 0.9 seconds and we ended with 1 second. So the total time duration here is 0.1 second. And we can see also that we have full 6 waves of voltage. So the total waves in 1 second will be 60. So our frequency here is 60 Hz, and this is exactly what we need. In this slide, we will find the full load three-phase output, voltage, and currents. Also here we can find the full load three-phase output of only voltage. For every phase we can find in 0.1 second we have 6 full waves for each phase. So the frequency also in the load side is 60 Hz. We can use the transformer to step up or step down this voltage. The same here for the full load three-phase currents. Here we go for the last part of our system design, which is system protection. System protection is one of the most important parts of any electrical system design, as it can prevent crises on human and animal lives. Also, it can protect huge and expensive parts of the system. This protection can prevent the overload and also the short-circuit issues. And we can use several tools to protect any electrical system. And in our case here, we can use overcurrent relays, DC and AC circuit breakers, fuses, surge arresters, and many more. And we will see which components we used in the next slide. Our protection system consists of many components like surge arresters over HPV string that protects the system from surges and transient voltages. Also DC circuit breakers or fuses with 25 ampere rating, and this is independent on the load side calculated. So it's connected with HPV string, and also DC circuit breakers or fuses with 180 ampere rating connected with HDC AC inverter, and it's also independent of the load side calculations. And finally a three-phase miniature circuit breaker with 800 ampere ratings in the main load panel. And in the DC circuit breakers and fuses, it's commonly used the fuses, not the DC circuit breakers, because it's not easy to find DC circuit breakers with required rating. In the next slide, we'll see our system protection. In conclusion, this study shows that it could be a very good solution to have this PV system in St. John's, especially in the long run. It will be more economically than we only have the source from the grid. But still, This system could work much better in other places known for the high amount of solar energy. Thank you for your listening, and we are ready for any questions from you.